Okay, so today we're going to be looking at the first strategy, or one of the strategies, one of the simplest strategies for calculating probability. This can be used with both theoretical and experimental probability at times. So we'll do some examples, and this is just literally counting and sometimes making an organized list of some sort. Now, we'll be doing a different type of counting, a specific type of counting, and ways to look at probability in certain ways next class as well, or next online class as well. But today we're just going to be looking at examples as to when you would be able to use counting as and/or an organized list as a strategy for finding the probability for certain situations. So, the first one, and the kind of really common one that comes up, and really, whether you like it or not, in a way, a lot of times people who make errors don't actually want to do the full counting or organized list and then kind of make errors. So an example is rolling a pair of dice. Okay, so 2 different dice. Each of them, remember, has numbers 1 through 6 on them. And these are fair dice, so the assumption is that there's no more chance of rolling any number on one than there is on the other. Okay, so for example, we might find the probability of rolling a sum that is less than 5. Well, let's say less than or equal to 5. So, in other words, the sum is less than or equal to 5. Okay? So, we're looking at something where we're looking at a pair of dice and the probability of rolling those 2 dice and the sum when we add those 2 together. So, remember, this is adding the 2. And we add those 2 numbers together, we get a sum that is less than or equal to 5. So our strategy is going to be make kind of an organized list. And I'm just going to indicate that I'm looking at 2 different dice. So I'm going to use 2 different colors for the 2 dice. So this purple one will be die 1, okay, what I roll on die 1. And this green color will be what I roll on die 2. Okay, so what I'm just going to do is kind of organize what I could do. So one thing I could do is I could roll a 1 on die 1. And then I could also roll a 1 on die 2. Okay, now I like to do this in kind of a certain order, so I'm going to stick with rolling a 1 on die 1. But then I could also roll a 2 on die 2. I could roll, again, a 1 on die 1, but because I have up from 1 through 6, I could roll now a 3. Okay, I could roll a 1 and roll a 4. Could roll a 1 and roll a 5. Or I could roll a 1 and roll a 6. Okay? So with 1s on die 1, those are all the options I have. Now, I can't roll a 1 and a 7 because, again, this is just each die is only 1 through 6. Okay, so now I'm going to keep going, and I'm now going to say, what if I roll a 2 on die 1? Well, I could, again, and I like to order them kind of in order still so that I can tell where I am. 2, 1, and of course you don't have to organize it the exact same way, just as long as you're coming up with all the options. 2, 2. And just kind of 2 on all of this organized piece here. And then 2, 3, 2, 4, 2, 5, and 2, 6. Okay. And by the way, doing all of this, showing this, is showing your work for how you're figuring out the solution to. And again, this is a theoretical probability, not an experimental probability. Okay, so I could also roll a 3 and I'm going to have the same options available for the second die, the one represented by green. So 1, 2, 3, 4, 5, and 6. Okay. I could also roll a 4 on the one that is purple. Okay, and so because these are different dice, I could roll 1, 2, 3, 4, 5, or 6 there. Okay, and I also have the option of a 5. Okay, and 5, 1, 2, 3, 4, 5, or 6. Okay, and the very last possibility, because it's only a die that goes 1 through 6, would be 6 on on the purple die, and then either a 1, 2, 3, 4, 5, or 6 on the die that's represented by green. So there are all of our possible outcomes. So remember, when we're finding a probability of anything, we're going to look at our total number of outcomes. Remember, it's going to be whatever it is over the total outcomes. So the outcomes in the event divided by the total outcomes here. So our total outcomes, I had 6 here, 6, another 6, another 6, another 6, and another 6. So basically this is a 6 by 6 grid, so I had a total number of possible outcomes of 36. Okay, 36 different ways I can roll these 2 dice. And now what I'm going to do is I'm going to look for sums that are less than or equal to 5 here. Okay, I should probably actually turn that light on. So 1 plus 6 is larger than 5. 1 plus 5 is, I'm sorry, no, 1 plus 6 is not, I apologize, it was less than or equal. So forget that one. Let's just fix that there. Sorry about that. I forgot I had said less than or equal. So less than or equal to 5. So let's fix that real quickly. So what we want is anything that adds up to less than or equal to 5. So 1, 6 will not be part of that. I'll just kind of change the highlighter color. We'll go with pink. So less than or equal to 5. 1 and 1 would do because 1 plus 1 is 2. 1 and 2 would work because 3. And then 1 and 3 would work because it's 4. Now it says less than or equal to 5, so 5 does count. So those 4 in pink get counted. 2 plus 1 also counts because it's 3. And 1 plus 5 does not count here because that's 6, so that's higher than 5. And that is not an option. 1 and 6, as I said before, is not an option either. 2 and 1 is 3, so that does count. 2 and 2 is 4, so again, that's less than 5. And 2 and 3 equals 5, so that's an option too. 3 and 1, yep. 3 and 2 is equal 5, so that also counts. But nothing more in this 3 plus 3, 3 plus 4, 3 plus 5, etc. will be larger. 4 plus 1, yes, it is equal to 5. All of the rest of these, no. And at this point, every one of these other ones are going to be larger than 5. So we have all the ones that are less than or equal to 5, and then we just basically count them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have, out of those 36 options, we have 10 options out of the 36, which if we were to reduce it was 5 and 18 options. So there would be your probability. If you wanted to grab a calculator and calculate that either in decimal or percent form. Sorry about our dog. Calculator right working. So if we wanted to calculate that in decimal or percent form with a calculator, we would just take 5 divided by 18, which in just a second here, because I seem to have managed to not be able to find my calculator. There we go. So when we do 5 divided by 18, we get about 0.27 repeating. So approximately, we would call that approximately 0.28 or so if you wanted to find it in decimal form, or around 28%. if we rounded that to the nearest percent. Okay, don't worry too much about doing that in all of the problems, but if we were actually at school, I would probably ask you to do a little bit more of that, but right now it's not actually a possibility. All right, so that's one example of counting strategies. That's probably the one that's going to take kind of the longest amount of time. So the second one I'm going to do is actually a counting strategy where you're probably pretty familiar with it, just like using a tally sheet. You might use this a little bit more when it was theoretical. Okay, so, experimental probability. So, I'm going to do that. I have here a bag, and in that bag, I have green Myconikes, I have yellow Myconikes, I have pink Myconikes, I have red Myconikes, which might not look all that different for you there, and I have orange, orange Myconikes. Okay, so I have all of those Myconikes in there, and so I'm going to make a tally sheet as to which one I pick out. And I'm not going to know, this is going to be experimental probability. So I'm going to try to find a probability based on my experiment. It may or may not actually match the theoretical or the actual chance when the number of picks gets really, really extremely large of actually picking them out. So I'm going to pick, let's go 20 times. Okay, so find a probability. And I'm going to say, let's find the experimental probability of picking, let's go a little bit wild, red or yellow. Okay, so we're going to say either picking this or picking that. Okay, so I'm just going to shake up my bag, and I'm going to pick one out, and I picked a red. Okay, so I'm going to start my tally sheet, and I'm just going to give myself the option of picking red, or I'll put the red and the yellow over here because those are the two we're looking for, and I'm going to say green and pink and orange. Okay, and I'm going to go with 20 pulls, so I'm sorry that I can't share the Myconikes because they are yummy. I picked an orange. So there's 2. And then I'm going to pick out another one, another orange. So I picked out that one over there. And I picked out another red. So here's a red, and I am putting these back every time. So obviously if I continue to just keep them out, I would probably know the exact actual answer. There's a yellow. Okay, so yellow. And we're at 5 picks. And then green. So 6. Green again. So that's 7 picks. Red again. So that's 3 on the red. Orange. Or pink. I'm starting to feel a little bad for it. Another red. Green. Okay, and where are we? 5 and 6, so we're at 11. Yellow. That's 12. Ooh, pink. So pink was in there. 13. Looks like another pink there. So 14 picks. Orange. So we're at 15 picks. Right. 4, 6, 12. Yep, 15. Another orange. So 16 picks. A yellow. That's 17 picks. An orange. That's 18. Okay, 2 more and we're done. Yellow. So 19. And orange, that gave me my 20th pick. So we know that my total in the experiment was 20. So the probability of red or yellow okay, in this case, would be out of 20. Okay, and then I just count my reds and my yellows because that's the experiment that I have. That's what the data I have. I don't actually know what's in the bag. So there were 4 red in this case and 4 yellow. So the probability of picking red or yellow in this case would be 8 out of 20. So this would be the same as exactly, 4 out of 10, or never mind, exactly 40% or 0.4. Okay, now if you want to see what's actually in the bag, that is not actually what the numbers were. I'm actually not entirely sure what the numbers were, and I don't want to spend too much time on it. But when we look at what was actually in the bag, 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 22, 23. It looks like there were 24. And the actual truth was there were 3 out of 24, The actual, you want to know, sorry about my dog again, the actual red or yellow, so the actual probability, or, well, I really shouldn't call it actual, it's the theoretical probability, would have been out of 24, and it would have been 1, 2, 3, 4, 5, 6, 7, 8, 8 out of 24. So you'll notice we weren't exactly accurate there because the actual probability was actually a good bit, well, not a good bit, but a little bit. 8 divided by 24 here is about 33%. So, okay, it's a little lower there. But that just is because I picked out a little bit more, just like, a little bit more red or yellow. Probably on the yellow end where I picked out a little bit more than would have been expected. Had I done that thousands of times, I would have gotten a lot closer to that 33%. But I'm pretty sure that you don't want to go over that thousands of times. And of course, you're welcome to fast forward if you haven't already, any portion of this that you like. Okay, so I'm going to do one more example, and this one's kind of where I have a room. Okay, so this is an example of a type of area model. So this is, I guess, what's example 2. So up here was 2, and here is then the third one. So counting using an area model. Okay, and in this case, there are multiple types of area models you can use for figuring out probabilities of different things. Combined probabilities also can use area models. So there's kind of my room, though. So we're going to look at this floor plan. And let's figure out maybe the probability if you land at random. So this is going to be theoretical. And notice all of these sizes of the boxes in the rooms are the same. So it should be equally likely to land in every box. In any of the boxes. Okay. So we're going to figure out the theoretical probability of landing, let's say, in the library. Okay, and one random time. So one random trial. Okay, so if we just do it one time, if we go one time and kind of randomly pick a spot, how likely is it that that's going to be in the library? Now, if you go through this, you can actually count through and figure out how many these are. And sometimes I do that, but right now I know it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 down, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. So this is a 10 by 10 grid, which means there's a total of 100. So the total boxes is 100. So it'll be library boxes or library squares over total squares. Okay, and the probability of landing the library, now this one I am going to count, and I'm just going to kind of count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 that were in the library. So that's 18 out of 100. So in this case, this would be 18% or 0.18. All right, so those are the 3 examples. So now I'm going to have you, the end of this assignment, and to do some problems similar to this and to please show work this time, because I think some people are not sometimes. And it's kind of important here. But I might try to give you an option about like making your own kind of experimental one or doing one that I give you. We'll see on that, but hope you all have a fabulous rest of your day. And those of you who are seeing this on Friday, enjoy your weekend. Bye-bye.